Welcome everyone to today's webinar. It will be a very interesting one as we will be talking about some very exciting new results that were recently published about Enceladus. And today we have Thomas O'Sullivan, who will be presenting. He is the co-author of the paper that is now in the chat, so the link to the paper is in the chat. Tom is a PhD student in his second year at the University, the Freie Universität from Berlin, so the Free University of Berlin, in the Department of Planetary Science and Remote Sensing. Before his PhD work, he was at he did a master's degree at the International Space University in Strasbourg, so he's been around a bit. His research focuses on Enceladus, of course, and we will hear about that today, and the chemical composition of the plumes and that Enceladus ejects from below its surface. He does that under the supervision of Frank Postberg and Nozer Kawaja, also at the Free University, and he's also collaborating with Partho Bera from NASA Ames. Tom likes to get his hands dirty by doing simulations experiments in the lab of Enceladus's hydrothermal systems and connecting the results to the available data from the Cassini mission using quantum chemistry-based analysis. So he has both the practical lab experience as well as the modeling experience. Today he will present new results that we just mentioned, a new paper that came out very recently. But also Tom is very much involved in the Europlanet community, and he just got the position of co-chair for our Europlanet Early Careers Network. So that is very good. But now, Tom, the floor is yours. Go ahead.
Excellent.
Yes.
Thank you very much, Martin. Good morning, everyone. Thanks very much to Europlanet for having me. I'm going to talk about this new study where we detect a range of new organic compounds in an old Cassini data set that we've reanalyzed with new methodologies. So I'll just acknowledge all of the co-authors that contributed to the study. It was really quite a long process and quite a lot of analysis. So we're really pleased with the outcome. So I'll begin by giving a bit of context and taking you back 30 years to 1995. Now, in 1995, there were only two confirmed bodies in the solar system with liquid water. One of them, of course, is Earth, so that's cheating a little bit. And the other, Europa, one of the Galilean moons of Jupiter. But as we've begun to explore the solar system in more detail, particularly in the outer solar system, we found that more and more bodies play host to liquid water beneath their surface. Indeed, now that there are three of the four Jovian Galilean moons, so Ganymede, Callisto, and as mentioned, Europa, all possess subsurface oceans, as well as Enceladus, one of the small moons of Saturn, which I'll talk about today. Titan, another moon of Saturn, but a lot larger than Enceladus. And most recently, now we think that Mimas, another small moon of Saturn, has a very young ocean beneath its crust. But that's not all. These are only the sort of confirmed or very confident detections of subsurface oceans. Depending on who you ask, you may have different bodies included in that list, but certainly there are many others now that at least could theoretically have a subsurface ocean, or at least the presence of liquid water, if not an ocean. Or there is already some limited evidence for subsurface oceans on these bodies. So you have the Uranian moons, some other small moons of Saturn, and even as far out as Neptune's moon, Triton, and Pluto as well. Now, of these bodies with liquid water, only one extraterrestrial ocean world has had its subsurface material sampled, and that was Enceladus by Cassini. So it's a really, really good sample, a good example of the chemistry that might be going on in all of these subsurface oceans. And it's fair to say that the chemistry of Enceladus is by far the best characterized of all of these bodies, thanks to Cassini. So this is a beautiful image from Cassini of Saturn. It's backlit, so the sun is behind Saturn there. And you'll see a sort of extended faint halo around Saturn called the E ring. This is a small, this is a ring of small ice grains largely sourced from Enceladus, which you can see on the left-hand side here in the center of the E-ring. And interestingly, you can also see the bright speck just beneath the E-ring here, which is Earth as well. So it's a really, really nice image that was taken by Cassini. Now, the Saturn system is fascinating. It's rather complex. It's got a series of rings, which I'm sure you're familiar with, as well as several small shepherd moons within those rings. Moving out, we have some larger moons, increasing in size from Mimas, Enceladus, Tethys, Dione, out to Rhea, and beyond that, out to Titan. And a lot of these moons are situated within the E-ring, which, as I've mentioned, is the kind of depository of ice grains from Enceladus. And in the E-ring, these particles spread out over the course of many, many years, up to centuries, as you move further out, which means they're subject to a number of different processes, particularly space weathering effects, which may alter their size, their morphology, and critically their chemical composition. Now, the Enceladus plume is the source of particles for this E-ring, and the Enceladus plume was discovered by Cassini soon after it arrived at Saturn in 2004, and it observed these jets being emitted from the south pole of Enceladus. So you can see on the left-hand side this sort of bright region of the image. This is the densest part of the plume, and you can see here a close-up of some individual jets emanating through the crust at the South Pole. And I'll talk a bit more about the plume later on. Now, most of what we know from Enceladus came from the Cassini mission. So we know that it has a thick-ish ice crust, so sort of 20 to 25 kilometers thick is the current estimate. That's across most of the globe as an average. There are some regions where it's thicker and some where we believe it to be thinner as well. Gravity measurements from Cassini are consistent with a rocky, porous core with a silicate outer layer and an iron nickel inner layer. And it's quite a low density for a core of that composition, which leads to the implication that it must be slightly porous. So you have water feeding into cracks within the core. You can think of it as sort of a rubble pile of almost gravel-like material. And that takes up the bulk of the moon's volume, around 190 kilometers in radius. Above the core, Enceladus is home to a global subsurface ocean, again, varying in thickness depending on the ice crust, but between 10 and 25 kilometers are the current best estimates, and with a pH of moderately alkaline, 9 to 11. At the seafloor, one of the most interesting facets of Enceladus is its hydrothermal vents. These are high pressure, relatively high temperature regions of the ocean where you can have complex chemistry occurring, enabled by these higher pressures and temperatures than you would otherwise get on a world so far away from the sun. And the pressure can increase as you go deeper into the core, enabling different kinds of chemistry, we believe, and the temperature with that as well. Now, at the South Pole, this is where the crust is a lot thinner, probably less than 5 kilometers thick in places. And for this reason, we believe that the plume has broken through this crust and is ejecting actively material, so subsurface material into space in the form of gas vapors, and ice grains containing frozen ocean material. Now, Cassini was an outstanding mission, launched in 1997, arrived at Saturn 7 years later in 2004, completed 23 Enceladus flybys, of which 5 flew directly through the plume, and of course also featured the Huygens lander, which was the first landing on a moon other than our own, led by ESA. Now, Cassini had 2 instruments which were critical in analyzing the composition of material in the plume. Some other instruments contributed as well, infrared instruments, but these are the mass spectrometers, which gave quantitative analysis of material in ice grains and in the vapor phase. So on the left here, hidden on the spacecraft, it's in the reverse, but it's the ion and neutral mass spectrometer, INMS. Now this sampled the gas phase in the plume using electron ionization. Resolution of mass spectrometers varies depending on where you are, what mass to charge ratio you're at. But for most intents and purposes, had a mass resolution of about 100, which is pretty good, and a range of 99 atomic mass units for the gases. The cosmic dust analyzer analyzed the composition of ice grains by colliding with ice grains at hypervelocities, so greater than around 1 kilometer per second. These hypervelocity impacts, and I'll come on to talk about these a bit later, fragment and ionize compounds contained within the ice grain. And these can then be analyzed by a mass spectrometer by their time of flight, which depends on their mass to charge ratio. And this extended in most cases up to 200 mass units, although some particular flybys use different operational modes, which lowered the mass resolution, as I'll talk about later on. Now, I'll briefly discuss the very interesting results from INMS. It's not really the focus of this paper, but it does give us a lot of context about the potential habitability of the Enceladus subsurface. Now, all of these compounds have been detected in the gas phase with fairly high levels of confidence. Most recently, a paper from last year discovered the presence of hydrogen cyanide, which has implications for the kind of prebiotic reactions that could take place within the bulk ocean. Now, the cosmic dust analyzer, this is the impact ionization instrument, as we call it. So this was sensitive to ice grains ranging in size from just a few nanometers up to a few micrometers, which is pretty handy for the particles in the plume. Now, the CDA had a series of electric grids at its entrance, which gave information about the particle's size and its trajectory in one plane. Now, when you have an ice grain incident into this instrument, it will collide, as you can see from the animation, with the back plates here, which will ionize and fragment molecules embedded within ice grains into ions, electrons, and neutral compounds as well. Now, being a mass spectrometer, we only measure the ions that arise from these impacts, so we're blind to the neutrals. But luckily, we do get a significant ionic composition as well. Now, after impact, these ions are subject to an electric potential and accelerated toward the mass analyzer in the center. Here, their time of flight is recorded and converted using sort of geometric fitting parameters into a mass spectrum, which plots the mass to charge ratio against the intensity of ions arriving. So you think of it as the number of ions arriving at the instrument. Now, the kind of mass spectrum that you get from these ice grain impacts depends particularly on the velocity at which you impact the ice grain. So at the lower end of the velocity scale, so around 6 kilometers per second and below, you see extensive water clustering, which is the grouping of water-derived ions together. Water is a polar molecule, so it likes to stick together quite well. And this causes signals highlighted in blue here in the spectrum at various intervals throughout the spectrum. And we'll also see high mass features from our embedded organic compound if they're present, because we don't provide that much energy to fragment it heavily. As we start to increase the impact velocity up to around 10 kilometers per second, we reduce the extent of water clustering. So you can see a drop off in the intensity of those blue peaks as you move to higher masses. The more energy you provide, the harder it is for ions to stick together. And because you provide it with more energy, you start to see greater extents of fragmentation of your organic compound. So you see lower mass features as you begin to shatter that molecule a little bit more. And at the highest impact speeds, which we'll talk about in this work, the fastest flybys of Cassini were at 18 kilometers per second through the Enceladus plume. Here we see significantly reduced water clustering. So this gives us a nice view of the intermediate ranges. It can reveal features that may have been obscured at lower masses. The challenge, however, is that you are really inducing significant fragmentation at such energies. So you start to really break your molecule down to lower mass structural features, but you can still glean some information from this based on the features that you see. So you can kind of take all of those features in context of one another and begin to build back toward the parent molecule responsible for those fragment ions. So in essence, the fragmentation pattern that we see in the CDA mass spectra depends primarily upon three things. Of course, the species that is present in the ice grain, different organics will fragment differently. And the concentration matters as well. If you have very low concentrations, you may not be above the detection limit of that instrument, and so you're blind to low concentrations of compounds within the ice grain. And as we've just seen, the impact velocity as well also has a significant influence upon the mass spectrum. So I'll dive into now some of the previous results of Cassini and try and build a picture of Enceladus as a probably habitable world based on a lot of these results. So one of the early indications of a global salty subsurface ocean came in 2009 from Frank Posberg. Here, both in Saturn's E-ring and within the Plume itself, CDA detected a population of ice grains rich in sodium. You can see here a typical mass spectrum of a sodium-rich ice grain, so-called type 3 ice grains. Whilst sodium salts are the most dominant, we also see some other salts in these spectra as well. We see potassium, that's K plus at around 39. We see carbonate compounds, CO3. And we also see bicarbonates as well. Now, you'll notice that we don't see ions like calcium or magnesium so far. Work is ongoing to try and dig deeper into these mass spectra, but that also may be a consequence of the geochemistry of the Enceladus subsurface. Another detection, inorganic detection, was of silica, that's SiO2, silicon dioxide, in the form of nanoparticles detected by CDA. Now, in this scenario, silica nanoparticles only form from the slow cooling and recrystallization of dissolved silicate. Dissolved silica only happens at high pressures and high temperatures, consistent with the seafloor environment of Enceladus. And then as those silicate compounds dissolve in the hydrothermal systems, they rise to the ocean, cool, recrystallize, and are rejected into the plume. This is an area where there's a lot of research is ongoing, both modeling and experimentally, to kind of verify the type, the extent, the power of hydrothermal activity at the seafloor. One of the most recent detections in 2023 was of phosphate compounds. This is very important in the context of habitability. Phosphorus, of the 6 elements thought to be essential for life, so C, H, N, O, P, and S, of those, phosphorus was always thought to be the bottleneck for life on ocean worlds in the outer solar system. But it turns out that actually Enceladus probably has quite high concentrations of phosphate dissolved in its ocean. So here you can see an average of 9 phosphate-rich spectra taken from Saturn's E-ring. And you'll see here a sodium hydroxide feature supporting the idea of a moderately alkaline ocean. And you'll also see 3 characteristic features of phosphate minerals, sodium phosphate minerals. Now, these configurations of phosphate, these sort of chemical formulae, if you like, are supported by both laboratory analog experiments and quantum chemical calculations. A possible source of these phosphates is from the calcium minerals at the seafloor, where calcium is locked up in seafloor minerals, and sodium phosphate becomes more stable in the ocean. The concentrations are enhanced, we believe, relative to Earth's oceans, probably due to the consequences of phosphate chemistry beyond the carbon dioxide snow line, so beyond the point at which carbon dioxide becomes solid in the solar system. And this has consequences for the availability of carbonate and phosphate species within the bulk ocean. That's the inorganics. On the organic side of things, we've seen a really diverse range of compounds being emitted in ice grains from Enceladus. They span a range of chemical properties from their polarity, their mass, their solubility, aromaticity, and their saturation. So really a diverse subsurface chemistry is indicated by this range of properties. Now, one of the most interesting facets was the detection of what we call macromolecular fragments, so high mass organic molecules that have been fragmented in CDA mass spectra that lie beyond the nominal mass range, but we do see the fragment ions that are produced by their high-speed impacts. So we think that these are refractory organics, insoluble, and probably suspended in a layer at the top of the water surface. Here, they can be sprayed up into small particulates into the vents by bursting of bubbles at the water surface. These organic cores then act as nucleation centers for the condensation of water vapor onto them, which is how they become embedded in ice grains despite their insolubility. This is also in agreement, interestingly, with data from the ion and neutral mass spectrometer, which also detects aromatic compounds in a similar fashion to this. And the structure of these organic compounds is probably something a little bit like this. So we don't detect an exact molecule in these macromolecular fragments, but this is the kind of structure we expect the molecule to take. And this is consistent, again, with laboratory analog experiments. You'll note that this is closer to the insoluble organic matter that we see in carbonaceous chondrites and in meteorites, rather than polycyclic fused rings, polycyclic aromatic hydrocarbons with fused aromatic rings. And again, that's consistent with the patterns that we're seeing in these mass spectra. On the smaller mass side of things, I've shown the spectrum earlier on when we were talking about the velocity. This was one of the spectrums that really indicates the presence of low mass organic compounds. You can see here some low mass organic features at around 29, 31, 43, and 45, as well as again at higher masses coming off of those water cluster peaks, which begin to obscure things at higher masses. Now, these organic molecules include both oxygen and nitrogen-bearing functional groups, as well as low-mass isolated aromatic compounds. Now, these, again, we don't detect exact molecules here. We detect the functional groups. We can predict the fragmentations of these organic molecules based on their functional groups. And the features we see are in agreement with these kinds of structures. Now, these are relatively soluble, polar organics, and these are found at quite high concentrations, parts per million levels within the E ring. Now, the data set that we use in our new paper was previously analyzed in a little bit of detail, but not in a lot of detail. And this is a very unique data set from Cassini. It was recorded in the E5 flyby in 2008, which you can see the ground track of here on the right-hand side. The E5 flyby traversed directly over all four of these fractures called the tiger stripes in the south pole of Enceladus. And this is where we believe the plume is emanating from. It's made up of a mixture of high velocity jets powered by the supersonic emission of gases, as well as more diffuse sources which emit compounds and gases, ice grains and gases at a lower velocity. Now, Cassini CDA was not designed to handle particle fluxes as high as they were in the densest part of the plume. But fortunately, a very, very, very nice flight software update was applied, allowing a unique operational mode where we have a reduced mass range down to around 103 mass units from 200. In most cases, there are some exceptions, as well as the lower resolution as well. But that enabled a higher recording rate, so we can capture more ice grain impacts per second. Usually, in the standard operational mode, we get one impact per second. That's the time for the ions to be analyzed, the signal to be processed and filtered. But in this case, we increased the recording rate up to 5 impacts per second. So we get a much much nicer compositional view of the plume. This is the trajectory of the E5 flyby in purple here on the left-hand figure. So you can see it comes down over the equatorial regions and then passes over the South Pole, some kilometers from the South Pole. At closest approach, it was just 21 kilometers from the surface. You can see the data set that we're interested in here is these type 2 ice grains in the center, highlighted in red. The gray region here, this is the dense plume region corresponding to this thick purple line in the trajectory here. So this is the data set that we recorded during the flyby of the densest part of the plume. You can see before around 15 seconds from closest approach, this is the background flux of ice grains from the E-ring, which then becomes enhanced as we enter the denser regions of the plume. And in the densest part of the plume here, you'll see that we get no useful spectra, just simply because the particle density was too high and really complicated collaboration and analysis of mass spectra. Now, the first thing that we do in this data set is we're able to verify some of the detections of organics that we made previously in the E-ring. Now, we know that the distribution of organic compounds in E-ring ice grains is closely correlated to their proximity to the Enceladus orbit. So we increase in number density as we move closer to Enceladus. But it's unclear exactly how much these grains may have been altered by space radiation effects. E-ring particles persist for many, many years, depending on their radii. And during this time, they're subject to UV, perhaps electrons and ions from Saturn's magnetosphere as well. And this can cause chemical changes, can cause photodegradation or even photosynthesis. The photolysis, we would say, of organic, further organic molecules. There's some really nice work on this from Lenz Noehler and Grace Richards recently. And so the long story is that we couldn't verify whether these E-ring ice grains were products of space weathering or whether the compounds we see were unaltered from their time in the Enceladus subsurface. Unfortunately, in this fresh plume data, we detect similar spectral features as we did in the E-ring. So we see these characteristic aromatic molecules, which are probably connected to non-alkyl substituents. So that's non-carbon chains attached to these aromatic rings. And even at these high impact speeds, we're seeing these aromatic features corresponding to intact rings because it's such a stable structure. It's really, really hard to fragment aromatic rings completely. We also see features characteristic of oxygen-bearing molecules, most likely carbonyls. One example that we give here is acetaldehyde. We see this peak at a mass of 45, which would correspond to protonated acetaldehyde, which is standard for these kind of mass spectra. And so this very well may be a molecular peak. Now, we also detect some functional groups that we hadn't seen before in E-ring ice grains. Here we see ester and alkene characteristic features. We give the example of this molecule here. This is allyl propionate. But again, these are just candidate compounds. We can't make exact detections of the molecules, but the compounds that we give in this presentation and in the paper as well have quite nice spectral matches to the CDA mass spectra. Now, detecting esters is quite interesting. These occur in carbonaceous chondrites, but not in comets, which suggests that they may be formed from aqueous alteration in water-rich environments, so the surface of meteorites and indeed perhaps subsurface oceans. Alkenes are also quite interesting for hydrothermal chemistry. These are intermediates in many hydrothermal reactions. So really diversifying the prospects for subsurface chemistry on Enceladus. Similarly, we may also detect cyclic ester and alkenes, which is very interesting. One example that we show here is cyclohexyl acetate. So we may see diversity in the structures associated with the functional groups, as well as diversity in the types of functional groups that we're seeing. Another class of compound that we detect here are ether groups. These are oxygen linkages between carbon chains. Now, ethers are quite interesting. These can be precursor molecules to more complex compounds, some of which may go on to be involved in prebiotic reactions. And similarly to esters, these also occur in carbonaceous chondrites, but limited in comets, implying their synthesis on Enceladus. So this is really telling us that Enceladus is not just spitting out the organics that it formed from, but really is causing new chemistry within the ocean. Similarly, we also detect ethyl groups. These could be derived from larger polymeric compounds. One example that we show here is triethylene glycol monoethyl ether. You can see this is linked again by oxygen atoms in a polymeric fashion, which is consistent again with the types of reactions that we expect to be possible in the subsurface. And finally, one of the more tentative detectors in this paper are the presence of nitrogen and oxygen-bearing molecules on the same compound. So these mass spectra are a little bit more subjective because there are multiple ions that could be responsible for some of the peaks, including nitrogen and oxygen compounds. So for that reason, we can't make the confident detection here of NO-bearing molecules, but we can give a number of candidates that fit the mass spectral patterns. And we do that in the paper if you're interested in finding out those. So to summarize for now on the organics that we've detected, we analyzed fresh ice grains that were ejected just minutes, that were sampled just minutes after their ejection into the plume. And we see a diverse set of chemical compounds, which are probably involved in complex chemical cycles in the interior. Now, here we try to fit some of our detections and some previous detections and models of compounds into a chemical network. This is by no means exhaustive, and this is very much qualitative analysis. Some of these compounds we include that haven't yet been detected on Enceladus, amino acids or lipids, for example. We haven't seen those, but they would be, of course, highly significant in the context of astrobiology. So we include possible pathways from the observed compounds toward those. But really, the takeaway here is not any specific pathway, but it's that Enceladus is almost certainly home to a complex chemistry in its subsurface. We're interested particularly in its interfaces, so water rock, that's the sea floor, hydrothermal activity, the bulk ocean, what can happen with cold aqueous chemistry, and the ice-water interface, which may give us what we call freeze and thaw cycles, freeze-melt cycles. And really, this is an area that is prime for deeper investigations, both laboratory and modeling investigations. And you can kind of go in two ways from what we've learned about the chemical inventory of Enceladus. You can focus on detection methods. So that enables us to reinterpret CDA data in new ways, which is what we've done in this work. It enables us to develop lab analog techniques, be it for impact ionization of ice grains or for other models of hypervelocity impacts. And we've also developed theoretical methods, which I'll talk about very briefly in just a second as well, complementing our lab analogs. Or you can look at the subsurface chemistry, the subsurface processes that are creating the compounds that we believe we're seeing. Are these products of hydrothermal chemistry? How do we simulate hydrothermal systems in the lab? What happens as we cool hydrothermal products on their ascent through the ocean? And how does the chemistry change as these compounds enter into ice grains or the gas phase in the plume? Does this process alter the chemistry? Does the plume composition reflect the ocean chemistry? And altogether, this really provides feedback for the reinterpretation of existing data. This supports new observations, and it will help to guide the planning of future missions. Now, one of the theoretical methods that I mentioned in the previous slide is quantum chemistry, which is really where I work on. We assume that we can model the kinetic favorability of different fragment ions that are produced in these high-speed impacts using quantum chemistry. And this is an active area of research for us. We're looking at quantum chemical descriptions and quantum chemical models of how some of the compounds that we've detected here may fragment in these high-speed impacts. And what is the mass spectrometric response of such compounds in these high-speed impacts? So what's next? What's next? Enceladus continues to be an exciting destination for astrobiology research. And the more that we investigate Enceladus and Cassini's data, the more we believe that this is a habitable moon. But habitable, of course, does not mean inhabited necessarily. This is really where we're primed for more work. So we've not seen everything for sure in CDA mass spectra. We will continue to analyze these mass spectra and gain new insights all the time, even 20 years after Cassini arrived at Saturn. And as we learn more about the data, of course, we learn more about Enceladus, which feeds back into our interpretation of data. And this work is a nice example of that, where we've reanalyzed an old data set using new methodologies and new contextual information about Enceladus. Another upcoming observation is from James Webb, the James Webb Space Telescope. It's already glanced at the Plume with just a few minutes of integration time. And now there will be some investigations of the E-ring, the densest part of the E-ring from edge on, which gives quite a large column density for observations with spectroscopy, as well as lab simulations and modeling. This can be simulations of the hydrothermal systems of Enceladus, also the Plume formation, which I've mentioned, radiation effects in the E-ring and the Plume, the interior structure. How does the interior structure affect the available chemistry in the ocean, as well as the behavior of possible biologies in Enceladus-like environments. One of the projects that will aim to characterize further the chemistry of the subsurface is this new European Research Council project called the Analog Icy Moons Simulations, which is led by my friend and colleague Nazer Khawaja. Here we will investigate hydrothermal chemistry on the Enceladus sea floor and assess how that material is altered as it rises through the colder ocean, both organic and inorganic material. And really, we want to see the relationship between the compounds we have detected in CDA mass spectra to the processes that could be occurring in the subsurface. And perhaps most interestingly, the prospects for future exploration. Now, Europa Clipper is well on its way to Europa, which is the moon of Jupiter, also possessing a subsurface ocean and potential hydrothermal activity on its sea floor. Europa Clipper has an instrument called the Surface Dust Analyzer, which is similar to Cassini's CDA. And this will analyze the composition of dust grains, dust and ice grains emitted from the surface by micrometeorite bombardment, as well as potential plumes if they're there on Europa as well. There are some signs that there may be similar plumes on Europa. Moving out toward Enceladus and Saturn, there are a number of concepts in development. One of the most sci-fi-like ones is this exobiology excellent life surveyor from NASA and from JPL, which is a sort of snake-like robot capable of traversing through sort of crevices in the ice crust, as well as the Moonraker concept, which is a multiple flyby concept, which would again sample the plumes of Enceladus for their chemistry. But most interestingly, perhaps most pressingly, is ESA's large class mission. ESA's fourth large class mission will search for life at Enceladus. The current architecture is to consist of an orbiter and a lander, and to launch in the mid-2040s. The payload of this mission will need to answer the question of whether Enceladus is indeed inhabited by life. I hope that I've shown you how mass spectrometry can be a very, very useful instrument for doing that, for analyzing the chemistry and potential biochemistry of these ocean worlds. It really is an invaluable instrument for such investigations. And I'll close as we approach the Ministerial Council meeting in Bremen later this month with a quote from ESA's Director of Science, where an investigation into signs of past or present life around Saturn has never been achieved before and would guarantee ESA leadership in planetary science for decades to come. So with that, I'll thank all of the co-authors for their hard work on this paper, as well as the lead author, Nazair Kawaja, whose email is alongside mine there on the right-hand side. We have some funding acknowledgements as well, and you have links to the paper as well on the right-hand side. So thank you very much, and I'll look forward to taking the questions.
Thank you so much, Thomas. This was a really excellent talk, a very exciting topic. And we already have 4 questions lined up for you. So let's go straight into them.
Fantastic.
Yeah, so the first question is by Ben Edward. Ben asks, you mentioned water clustering present in your mass spectra. Could future instrumentation or calibration methods mitigate for the phenomenon and allow for more accurate detection of organics at the lower velocities, impact velocities?
Yes, and thank you very much for the question. It's an excellent point. And the answer really is that these future instruments will have much higher resolutions. So you can see, I'll just go back to some of the low mass organic spectra that I showed here. Here. Now you can see, again, that there's this extent of water clustering, and you see that our organic peaks are often very closely related to these water cluster peaks. And they're quite difficult to resolve in some cases. So by increasing the resolution and having better defined mass peaks, we can really differentiate between water clusters and peaks that are not water clusters, presumably these organic fragments. Similarly, with better mass resolutions, we can also see isotopes. We can do isotopic analysis with future instruments like SUDA and some concepts for future Enceladus missions, which again will enable the comparison between peaks separated by less than an integer mass, and you'll really be able to see the isotopic abundances, some of which would be characteristic of water, some of which may be characteristic of other contributing peaks at those masses, so carbon-based peaks, for example. We do use lab analogs as well to try and replicate these impact ionization mass spectra using laser desorption-based methods. And so we're really building up a good understanding and quite a nice reference database of these mass spectra where we can predict how already water clusters might affect our interpretation for compounds of interest. I hope that
answers the question. Yes, thank you. The next question is by Gurai, and Gurai asks, how do Enceladus and Earth conditions differ in isotope fractionations? Maybe methyl or hydronium ion. Could you exemplify, and what do we see its impact in the MS results?
Sure. So CDA was not capable of isotopic analysis. We just don't have a high enough resolution to do that kind of analysis. But some models predict, the fractionation of isotopes in the outer solar system is distinct with distance from the sun as a consequence of planetary formation. So there are isotopic ratios that we can look for, and there are isotopic fractionations that would even indicate a potential biosignature amidst other relevant data. So isotopic analysis is a really important mode of analysis for future missions, and is really one of our best ways of piecing together what isotopes are used by potential biological systems in such worlds. I can't talk about exactly how Enceladus and Earth differ. I'm not sure. Um, but certainly we're blind to isotopic fractionation in these mass spectra.
Okay, so there's definitely room for new measurements in the future. Next question by Adam Nawal. Thank you for a fantastic talk on a great paper. Do you believe the reason for no sulfur containing species being detected is because of sampling a lack of sulfur in the plumes or sulfur being rare on Enceladus? What is your take on that?
Yeah, thanks, Adam. It's a good question. In the case of sulfur, there may have been a detection of sulfur from INMS in the gas phase of hydrogen sulfide. It's not a unique interpretation, but it is generally expected that sulfur is probably present. It's probably present on Enceladus. It may be hidden by clusters in our mass spectra, and this is an area as well that we're looking into with new methods of analysis of these impact mass spectra. If we're seeing phosphorus on Enceladus, this is probably the scarcest of the six bioessential elements. So if we see phosphorus, we should be seeing sulfur as well. So it's a lack of detection is not a reason to rule it out. It may just be that we're blind to the particular forms of sulfur that may be present in these data sets that we have from Cassini, but certainly don't rule it out.
So, sorry, why would you expect to see sulfur if you see phosphates? What is the direct connection?
Phosphorus is cosmically less abundant than sulfur.
Ah, right, yes. Yeah.
So if we're seeing abundant dissolved phosphorus in the ocean, we should be seeing even more, in theory, abundant levels of sulfur.
Sulfur, okay.
So it's on an ongoing area that we're looking into.
Absolutely. Next question. Grace Richards asks, really cool work. Thank you. How do you determine the length of time that an ice grain has been in the space environment? Is it from the impact speed onto detectors or ejection speed of the ice grain, or both?
Yeah, thanks, Grace. So when we're talking about impact velocities here, the dominant contribution to that velocity vector is the speed of Cassini relative to Enceladus. So ice grains are probably ejected out at a few hundred meters per second, whereas Cassini is flying by in this case, 18 kilometers per second. So we don't infer the age of the ice grain from that, but in this case, it's more about the proximity to Enceladus. So the further out an ice grain is in the E-ring, the closer toward the outer reaches of the Saturn system, toward Titan, really, that an ice grain is, the older it is, the longer it has been in the E-ring. And it's been dynamically pushed outwards in its orbit. And we believe there are sort of gravitational dynamical areas of the E-ring which slow down ice grain migration as well. That can be due to sort of the sort of small charging of ice grains and their sort of pressure or their flux in the magnetosphere of Saturn balanced against gravitational forces. So there may be sort of non-linear mechanisms of ice grain migration, which complicate age analysis. But in general, the rule of thumb is that the further away from Enceladus, the older the ice grain.
Yeah, that makes sense, I guess. And it's amazing that Cassini flew by at like 20 kilometers from the surface.
It's
like a suicide mission almost.
It was incredible that we got data that they managed to update the CDA software to perform this kind of analysis. Really amazing engineering.
20 kilometers is only like twice the height of a normal airplane here on Earth, above the surface. Okay, next question by an anonymous attendee. Excellent presentation, thank you. If amino acids are present in the ocean of Enceladus, could CDA have been able to detect them? If no, what would be needed for their detection? Yeah,
thank you. It's a really good question. So it ultimately depends on the amino acid. So CDA's mass range in nominal cases was 200 mass units. And in this particular set of data, it was reduced to 100 to 125 in some cases. So most amino acids are above 100 mass units, with the exception of a few small mass ones, glycine, for example. So in theory, CDA can detect amino acids, but we don't necessarily know if the fragments that those amino acids would produce would correspond with water clusters and be obscured, or how stable also those amino acid compounds are for detection in the E ring, for example. So we're not sure if we have nothing to suggest that we have seen amino acids, but we've certainly seen related compounds, low mass amines and low mass oxygen bearing compounds, and the kind of volatiles that we're seeing are consistent with terrestrial amino acid synthesis reactions. So that's what we do in our lab is we try to replicate the mass spectra of amino acids and similar compounds of interest. So certainly instruments like Europlanet Suda and the next mission to go to Enceladus will be capable of distinguishing amino acids from isotopes, from fragmentations that we understand in detail. But the low mass resolution of Cassini in these, of CDA in these cases is not conducive to amino acid detection.
Great, thank you. Questions keep rolling in, which is great. So Fluvio Franchi asks, I might have missed it in the presentation, but have you considered the isotopic composition of carbon, oxygen, etc., and their link to hydrothermal vents or cold seep processes? What's the way forward with that?
Sure, thanks, Fulvio. So it's a similar answer. It's that CDA is blind to isotopic ratios. So we know that we expect certain ratios of carbon, of oxygen, of hydrogen, deuterium, for example, in the outer solar system. But we're really not able to characterize that with CDA, unfortunately. So it's hard to say. In the case of hydrothermal vents, you may expect some deviation from primordial isotopic ratios through this chemistry and sort of recombining, not recombining, or reactions of primordial molecules, as well as possible utilization by biology if it's there. But we don't have a way to tell that, unfortunately, with Cassini. But again, future missions will be able to do that kind of analysis, and we're pretty excited for that.
Yeah, we need to stay around for a while. Next question by Nat Leveau. I hope I pronounced that correctly. Besides detecting silicate particles, what is the other evidence that supports the hydrothermal system existence?
Excellent, thank you. Yeah, there's a few. I didn't mention all of the lines of evidence for the hydrothermal systems, some of which come from this vapor phase INMS data. So we're seeing molecular hydrogen in the plume, which is highly volatile, of course. So detection of active hydrogen in the plume implies it must be being produced constantly in the subsurface. And this is consistent with some hydrothermal reactions that we see on Earth, one of which is serpentinization, which is the release of hydrogen and methane as well, which is another gas that we see in the vapor phase. So the gas phase chemistry tells us a lot about that, and that's consistent again with laboratory simulations of these hydrothermal systems. There's some really nice work from Sakina in 2015 that dives into this if you're interested. The organic compounds that we see in ice grains as well are indicative of chemistry in the subsurface. We can't necessarily attribute it all to hydrothermal chemistry, but certainly there is this active chemistry that is altering Enceladus's primordial organic inventory beneath the surface, which could be hydrothermal, which could be in the bulk ocean, which could be at the ice-ocean interface as well.
Yeah, hope that answers the question there. We really need those eels going to take a look beneath the ice. There's one comment and one final question. Andrew Coates comments, nice talk. CAPS measurements of water clusters and other negative and positive ions relevant as well. Analysis still underway.
Yeah, we're
exclamation
very
mark.
excited. Yeah, I mean, Cassini's suite of instruments really, yeah, have to be taken in context together.
Yeah, 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 yeah.
When we put all these data sets together, we learn so much more about kind of
Absolutely. Yeah, yeah,
the
yeah.
Saturn system.
All right. One final question here by Aine O'Brien. Thanks for an amazing talk. Super interesting. You mentioned there were primary candidate molecules. Would the only way to be certain of their identity to have onboard standards in the mass spec? I assume this is only plausible for a sample return mission, or would the future mission to Enceladus be able to confirm molecular IDs?
Yeah, thanks for the question. So again, this is a consequence of CDA not being designed to do this kind of analysis. So CDA's low resolution and limited mass range means that it means it's very hard to determine molecular peaks, which would be the standard way of using mass spectrometry to determine the identity of a compound. To try and mitigate that, we do laboratory analog experiments that I've mentioned to try and replicate what these impact ionization mass spectra look like. So when we have more sophisticated instruments that are designed to do this kind of high particle density analysis, like Europlanet Suda, like the next Enceladus mission, we should be capable of really detecting mass spectra up to higher masses and with a much, much more enhanced resolution. So you don't necessarily need the onboard standards. We can do a lot with lab analog methods. And I mean, sample return, of course, is always the ideal case. But we believe that we can do a lot with impact ionization mass spectrometry in the Plume, a lot more than just what Cassini was able to do with a dedicated instrument.
Great. Thank you so much. Yeah, sample return. It's a bit of a stretch for now, at least. I don't see sample return coming from Saturn just yet, but we still have to manage that for Mars or other planets. But who knows in the future, of course. Or we'll just go there ourselves, you know.
Yeah.
Anyway, there are no more questions in the Q&A here. Mars sample return via Enceladus. Ben Edward is suggesting, yes, why not? We can suggest it. Write a proposal to ESA. So I think we are over the hour, which is a great time, I guess, to wrap up our session today. So thank you, everyone. Thank you for attending. Thank you so much, Thomas, for the wonderful presentation and all your work. And congratulations on the paper, of course, and on your co-chair EPEC assignment.
Thanks for having me. I'm really looking forward to getting started with the EPEC stuff as well. It's going
Absolutely.
to be a good time.
And thank you very much, and see you soon.
Thanks, Martin. See you later, everybody.
Thanks, everyone. Bye-bye.